Hi, welcome to this video. We'll learn about probabilistic cash flow analysis. And this video is a continuation on a bigger topic, which is how to handle uncertainty when dealing with cash flows and making economical decisions about engineering alternatives and projects. So in the first part of this topic, we covered the different methods of handling uncertainty and possibility of changing the values of some parameters. And we'll learn about sensitivity analysis and break-even analysis. Now, we'll learn in this video about probabilistic analysis, which in this case here, you have more information about the magnitude of the variability of your cash flow. So it's not just a matter of the range, like sensitivity. You are assessing the sensitivity of the outcome of the project relative to the change of some parameters or some parts of the cash flow within the range. But now we know, let's say we know the probabilities of the possible cash flows. We know what's most probably will happen, or what's the least probable cash flow that will happen. So that's kind of an extra information that will help us to do more elaborate analysis that will give us more insights onto the uncertainty that we have in the project. So just to give an example, let's say you have these investments, or you can say engineering project alternatives, A and B. And you can see here alternative B or investment B gives a higher average or mean value for its return. And the return here is 20% compared to investment A, which is 10% the average or the mean. So if you think about it, then just by looking at the mean value or the average value, you'd say I will pick investment B. But from risk perspective, B is more risky because there's more probability to be less than the mean value. So that area here to the left of 20% return, that's all bad news, because if you plan for 20%, there's a lot of big probability that you'll end up with 10, negative 10, 20, negative 20, even 30. But if you look at investment A, your average is 10%, which is less than 20. But you are more certain, and there is less variability here, so there is less risk. So it's typically like that in investments in general, is with higher return comes higher risk. So if you're gonna invest in stocks, it give you higher return, but it will probably also, you will be subject to high volatility and ups and downs. But if you're gonna invest in bonds, it's less return, but also it's less risky. So that's from trading perspective, but in also projects and alternatives, it's kind of similar concepts. So to analyze and to be able now to really pick which alternative and which investment, you can say, to pick, you will analyze both investments here, alternatives, using probabilistic economic analysis. So the first thing you need to do is you need to estimate the risk of each cash flow occurrence in the life of that investment or cash flow or project. And then you need to aggregate the risk here of each cash flow that happens over time to come until you get the risk of the overall worth or value of the project. And finally, assess the probability of the possible project outcomes. So you can say, what's really the possibility that I will be less than or equal to 0 present worth. So we'll see each one of these steps in the next slides. So when we estimate the cash flows, we'll not use any more crisp values. We'll not say my initial investment in that, and then you will have this return in this year, single value to represent each one of these. This is not the case now in this analysis. You will represent each one of the cash flow occurrences, your investment, maintenance, revenue, using 3 values. So every one of these will be estimated using optimistic estimate, pessimistic estimate, and most likely estimate, H, L, and M. So if everything goes well, then your cash flow, that specific cash flow occurrence at year five, for example, will follow that optimistic estimate. If everything goes terrible, then you're following the pessimistic estimate. And if everything is moved or as usually expected, then you will be following the most likely estimate. And then we'll assume beta distribution here for each cash flow occurrence, following these three parameters that we estimated. So now we will be able, for that beta distributed cash flow, we will be able to calculate the expected value of this cash flow at year end. So it's expected value of the cash flow at year end would be equal to this formula here. So the high, or the optimistic, plus 4 the most likely, plus low, or the pessimistic, divided by 6. So you can look here, we're giving 4 times the weight of the most likely estimate compared to the high and the low, or optimistic and pessimistic. So that's the expected value now, using these 3 entry values for every cash flow occurrence. And then you also be able to calculate the variance. So in probability, you always look for the mean or the expected value, and then the variance, which also will be related to standard deviation. But here we're calculating the variance as the difference, or the range here, which is the high optimistic minus low pessimistic divided by 6, because you have here 6 kind of weights assigned differently to the 3 different values, and then that will be to the power 2. So now you have, for every cash flow occurrence, these 2 values, probability values, the mean and the variance. So let's see an example here. So you have the 3-point estimates, meaning that L, M, and H estimates for every year cash flow for this project. You can see there is no much variability in the initial investment. You're pretty sure that will cost you that, but then the return is different based on for the worst case scenario, or the pessimistic, all the way to the best case scenario, which is optimistic. So we need here to calculate the expected value and variance of the above, in this case, not below, the above annual cash flow occurrence. So we will be basically applying these 2 formulas, the expected and the variance, for every cash flow in every year. So for example, in the second year, the expected will be low plus 4 times the median plus the high estimate divided by 6, and that will give us this value, 20,439. And then the variance will be the difference between the high and the low divided by 6 to the power 2. Of course, this is dollar value, and this is kind of dollar to the power 2. And we do that for all years in that project cash flow. So once you do that 3-point estimate of the cash flows, using the pessimistic, optimistic, most likely, now we will, as if we're doing now in the deterministic way of analyzing cash flow, we need to calculate the worth of the whole cash flow. Now we're aggregating the risk of the whole cash flow. So we're kind of moving from probability of every individual year or annual cash flow occurrence to the probability of the whole cash flow of the whole project. So we'll do that, assuming that here we were going to stick to the present worth method of representing the value of the project. And we'll follow here, the framework that we'll follow is the central limit theorem. So in central limit theorem, it assumes that there are the independent variables we have, and then when we add these variables based on specific assumptions, their sum will tend to be following a normal distribution, a bell curve. Even if the distribution of these independent variables do not follow a normal distribution. So you can see here different variables, everyone following different distribution, uniformly distributed, beta, skewed. So when you add all of these assuming that there is enough number of them, they're not like one or two, two or three. So like the larger the number, the more you're following the central limit theorem here. So the sum of these variables will be following a normal distribution bill curve. So to put it in simple words, what this implies to us is the mean of the sum. So the mean of the sum that distribute the normally distributed mu variable here. So this sum, the mean or the average of it, is the sum of the means of its variables. And then the variance of the sum is the sum of the variances. So to translate that, this happens here is the mean of the sum, so the mean here, the expected of the sum, the present worth of the whole cash flow, is the sum of the mean of the individual cash flows. But remember, we're discounting here, so we are accounting for the time value of money, so we're dividing by 1 plus I to the power n. So that's the expected value. So the expected value of the net worth of the whole project now is that value. So you do the sum of expected values we got from the optimistic, pessimistic, and most likely estimates, but you're discounting every year to the present by dividing by over 1 plus I to the power n. The variance of the sum will be equal to the sum of the variance, but now we're discounting it, but now because the variance here is to the power 2, then you are dividing by 1 plus I to the power 2n. So an I here is the risk-free time value of money. Risk-free here means you're not adjusting your time value of money to account for risk, because your cash flow is already accounting for risks by modeling the optimistic, pessimistic, and most likely. So this is the meaning of risk-free. It's just use the standard time value of money or minimum attractive rate of return you would use. And then n here, uppercase, is just the number of years in the useful life of that project or asset. So now we can, to summarize, you started with the individual years, optimistic, pessimistic, and most likely estimates. Crunch these into two values, the expected and the variance of each cash flow occurrence in every year. Add up the expected and variances of all these cash flows to end up with the expected and variance of the present worth of the whole project. And now your project net present worth is following a normally distributed distribution of probability here. Kind of mu now is equal to that expected of the present worth, and sigma of that the normal distribution is equal to square root of the variance. That's from a basic probability knowledge we learned in other courses. But you can see here that the area under that curve, like any probability curve, is equal to 100% probability, or 1. If you look at the mean here splits the curve or the bill shape symmetrically. So the area to the left, which means that the cumulative probability of being below or less than the mean will be 50%, and the cumulative probability, the area under the curve, to have the variable more than or the present worth more than that average will be 50% also, right? So the 100% is split equally to the left and the right of the mean value of that of the present worth distribution. And of course, you can see here, if you move plus and minus sigma, you will be within like confining around 68% probability here. If you move 2 sigma plus and negative, you're within 95 probability of being within that range of present worth. And then, of course, if you move to 0.3 and negative 0.3 sigma, or standard deviation, you will be almost 100%, 99.74%. So that's a quick review of normal distribution. But now, following the central limit theorem, now we have the attributes of a normally distributed probability of the present worth of the project. So let's apply this in this example. Continuing with it, part B of it, we want to calculate the expected value and standard deviation of the project present worth and setting I to be equal 15%. So this is what we had from part A, and these are the formulas we'll apply. So the first one will apply the expected of the present worth, and that's basically kind of analyzing a cash flow and bringing it to the present, but now analyzing not all of these values, just the expected values of them. And when you do the discounting here, you can see you'll end up with the expected of the present worth at 15% to be for 14,817. And we apply the formula for the variance, kind of your variance of the first part of the cash flow, which is the initial investment, is equal to 0 because there is no variance. All the values for optimistic, pessimistic, and most likely are the same, so there is no variance. So you can see here there is 0 here plus all of these variances, but now dividing by 1 plus I to the power 2n. So don't forget, you can see here the double the power between the case of the expected formula and the variance formula. Once you get the variance, then you can say that sigma, the standard deviation, will be equal to the square root of it. So that's my standard deviation of that present worth. So after now we have built that probability distribution of the present worth, we can now assess the different possibilities or outcomes of that project. So we will do that by using a distribution called the Z standard normal variable. So we are following here non-standard normal variable because our mean is not equal to 0, it's equal to that mu that we calculated. But to be able to calculate the different probabilities, it's easier to follow the Z standard normal distribution, which is the mean here is equal to 0. So we need to standardize our values that we got for the present worth, expected values. So for any value now we compare to that expected value of present worth, we need to normalize. And we normalize it here to be a Z variable, not X, which refers to the present worth. So the Z will be equal to X minus mu, the mean, divided by the standard deviation. And now when we say that the probability of present worth, or the variable less than a specific value in the non-standard form of normal distribution, it will be equal to phi, which is the cumulative probability of a value less than this Z, which is the standardized form of the X value here. And if I get this value, that cumulative probability, from the Z formula or the Z table, like we'll see, that will be equal to the probability that my present worth will be less than or equal to a specific value, X. So from the textbooks, we can get different different formats of Z tables, but this is typically what the Z table would look like. Some textbook will give you only the positive values. In this textbook, it gives you the negative and the positive values for Z. You can see here it expands or extends from negative 3Z, or negative 3 standard deviations, to positive 3 standard deviation, which is, you are already kind of within almost 100% of your cumulative probability coverage. So what we'll learn is we can solve any problem by using only the probabilities of the positive Z, because the bill shape here is symmetrical. So we'll see that very soon. So let's elaborate that a little more. So this is a positive Z value table. You can see here, this is how I can get the value of that specific variable. So what's the probability that that I will be less than or equal to 0.32, or phi Z equal to 0.32. Oh, this is phi, sorry. So phi, the cumulative probability that I will be within 0.32 value for Z. So if this is the mean for Z variable is equal to 0, 0.32 will be pretty close to it. So when I say phi Z equal to 0.32, it's basically the area under the bill shape to the left of the Z value. Now to read the table, you have to see it's the 0.32 is split between the rows and the column headers. So 0.32, 0.302, so it's equal to 0.32. Once you pin the column and the header, the row, then this is the value of phi, that cumulative probability. So this means that there is a 62.552% that the z, there will be, I will be less than or equal to that z value. Let's consider the negative value of the same amount of z, so negative 0.32. And now I'm looking at the other table, which is negative z values. So negative 0.32, negative 0.3, then 0.02, that gives us here 0.37448. But if I remember, the probability that z will be equal to positive 0.32 was 0.62552. And I notice here that when I add these probabilities, they add up to 1. And that's because the tables give you the probability or the area to the left, under the curve to the left of your value. So if this line here is negative 0.32, if I consider it positive, so the area to the right of it when it's negative is the same of the area to the left of it when it's positive. And this is why kind of this one here is equal to that value here that we just calculated from the previous slide, this one. So the area to the left of this value when it's positive is equal to the area of it right area to right to the value when it's now negative. And this is why we say when you add them together will be 1. So if your value here that you're dealing with is a negative z value, then you can say basically it's 1 minus the cumulative probability when z is the positive value. So you don't have to really deal with negative z tables. You just need to deal with the positive z table. So let's see this example here. Continuing with the previous example we dealt with, we covered part A and B. And we have 3 more parts here. The first one is what's the probability that the present worth will be equal to 0 or less. So it's kind of giving us the case where we will be worried because the present worth using our MARR equal to 15% is less than 0. So that's kind of the bad news for us. And we want to see what's the probability of bad news. What we did in part B is we figured out the mean and the standard deviation of the present worth probability for the whole project. And what we will do is we will now frame our part C problem here as what's the probability that the present worth under 15% interest or time value of money would be equal to or less than 0. That's what the problem asks for, right? So what's the probability that the present worth will be equal to 0 or less than 0? So that probability will be equal to the cumulative probability of the z variable is equal to x minus mu over sigma. And my x here is equal to that value, which is 0. And I'm having mu and sigma from the previous part. So that will be translated into what's the phi value of a z value of negative 1.5253. And like we said before, a phi or cumulative probability of a negative z value is equal to 1 minus the cumulative probability of that value, but now positive. So actually that one should be positive. So I will fix that. Here you go. And then, so again, that's something I will fix here. So that's positive, and that's here positive. So, so the positive z value now, if I look at the table, 1.5253, 1.5, there you go, 1.5, 253, so 2, and then 53 means I'm between 1.52 and 1.53. So my cumulative probability here of that value is between these two probability values, these two. So using interpolation, you can figure out the value that's between them, considering now that you're 1.5253 in the middle of 1.52 and 1.53. So I'll leave this for you to try yourself, but we ended up here with calculating by interpolation that probability of positive z value here. So now going back to the original point here, so probability of our present worth to be less than 0 would equal to 1 minus that value of probability. So at the end I will see that there is very marginal probability, around 6.4%, that my present worth or that project will not economically viable to me. So it's really small percentage here, and that's the key. That's what you're really looking for, is assessing the attractiveness of this investment for you, assuming that you have 15% time value of money or minimum attractive rate of return. Part D is asking for what's the probability now that the present worth will be less than the worst case scenario. So it's not something that will give us insights. It's more about plotting and really figuring out where is my worst case in that probability distribution, and the next part, which is where's my best case scenario in that probability distribution. So what we'll do is we'll calculate the present worth of our worst case scenario, and that will be our benchmark. That's what will be used to calculate the probability and the z and all of that. So this is just the cash flow calculation here for that worst case scenario using 15% discounting here, and that's the value we end up here. It's negative. So that's of course negative because it's a worst case scenario. You have very small values of revenue here. So your probability that the present worth will be less than negative that amount here will be equal to the z probability when the z is equal to this formula here. So now we're normalizing this value here to be negative 5.93. So z here is negative value, but if you remember in the tables, they only cover from negative 3 standard deviation, negative 3 to positive 3. So now negative 5.93 is, beyond the limits of the table, but remember the probability here to the left of a very, far away negative value, that's at the tail of the distribution, probability distribution. So the probability here is almost 0. So which makes sense. The worst case scenario is nothing bad, worse happen, compared to it. So there is less, very small chance or almost zero chance that you will experience worst case than the worst case scenario. And the best case scenario will end up with a similar conclusion. You will calculate the present worth first of that best case scenario. It will end up to be pretty big positive value here, and then you will use this value to calculate its normalized z value, which positive 7.45. So that's on the other side of the bill curve. It's very large, beyond the positive 3 limit that we experience or we see in the table. So this means that the probability that you will be less than that value is almost the area under the whole curve. So that's 100%. So in summary here, that's the probability distribution that we have been dealt with. We constructed using the 3-point estimates of all the annual cash flows of this project, and we kind of were interested into what's the probability, this is the real question here, what's the probability that the present worth will be equal to 0? And it turns out to be that small percentage here, 6.36. And we can also visualize here, where's my worst case? It's really far away in that tail, left tail of the bill curve. And then the best case scenario is really far to the right of that tail, the right tail of the bill shape of that normally distributed variable here, which is our present worth. So that's it. That's the probabilistic cash flow analysis. It requires more information that we have seen in sensitivity analysis. You need to know the probability kind of beta distribution that's represented by 3-point estimate, the optimistic, pessimistic, and most likely estimates of every annual cash flow of this project. But it will give you a lot of insights. You can have this probability distribution now and really figure out and see what's the probability of me having good news, which is, you know, probability that, or actually the probability of the bad news, because here that's the probability that the present worth will be equal to 0. But this area here is all of it is good news. There is a high possibility here around, you know, 95.6% that you will be happy with this investment because it will return more than you're asking for. All right, so thanks for watching. We'll see you in future videos. Take care of yourself and those around you.